So here we are in chapter 25, the last chapter for unit 6, and we're going to be talking about paired samples and blocks. Here, short homework assignment. I think you guys can all finish it by the weekend, and then we will move on to the unit 6 test, and we are almost there in preparation for the AP test. So only 2 more chapters left. So the objective is students will test hypotheses about paired data with correlated groups. So if you think back to chapter 13, when we talked about observational studies and experimentation and how to conduct those, one of the things we talked about was paired data and blocking. So data are paired when the observations are collected in pairs or the values in one group are naturally related to values in another group. Paired data arise in a number of ways. Probably the most common is to compare subjects with themselves before and after a treatment. So this is type of a pre-test, post-test. When pairs arise from an experiment, the pairing is a type of blocking. When they arise from an observational study, it's a form of matching. So we have blocking and we have matching. Blocking is from experiments and matching is from observational studies. Also remember that only one of these two has a cause and effect relationship, and that's from experiments. We never can say that there's a causal relationship from an observational study. So you might be thinking, how does a match paired treatment work? So if we were running an experiment and we had 2 different types of medications that we wanted to test out and see if there was a difference in those, or let's say we have a medication and a placebo, we might be wanting to run a block experiment or a randomized block experiment. So let's go back to the chapter 13 notes for a second, just to describe what those 2 are. Because if you remember, when we're grouping these or blocking these subjects together, they are not independent from each other. And because they're not independent, we can't run a 2-sample t-test. So when we say blocking, we're blocking when groups of experimental units are similar, and it's a good idea to gather them into blocks. And blocking is for experiments, what stratifying is for sampling. Both methods group together subjects that are similar and randomized within those groups as ways to reduce unwanted variation. So probably the most important purpose of control in any study is the attempt to reduce variation resulting from any variable other than the variable of interest being observed. We want to focus solely on what we can measure as opposed to all the other factors. Again, with blocking isolates the variability due to the differences between the blocks to highlight the differences due to the treatments. We use blocks to reduce variability so we can see the effects of the factors by separating the effects of the blocks themselves. The research randomly assigns subjects within blocks, and we call those randomized block design. So, for example, if we are concerned about the effect of grade level on our experiment, we could block by grade level, then randomly assign subjects within each grade level to the various treatment levels. If we're talking about matching, in a retrospective or prospective study, subjects are sometimes paired because they are similar in ways not under study. So twin studies are a good example. And this is what we call a matched pair design. Matched pair design creates blocks by matching pairs of similar experimental units. Chance or random assignment decides which member of a pair gets the first treatment. The other subject in that pair gets the other treatment. So the way your book describes this is if you look at Olympic speed skaters, one person is randomly assigned the inside track for half the race, and the other person gets the outside track, and then halfway through the race, they switch. Probably the most common type of matching is the before and after or pre-test, post-test. Each pair in the matched pair design is actually one subject that gets both treatments, one following the other. In that case, each participant serves as its own control. The order of the treatments may influence the response variable, so we must randomize the order of the treatments for each subject. I'm sure everyone is familiar with alcohol and driving studies. So if we were in school, they had that virtual simulator for the driving goggles that people could simulate drinking and driving. So let's hop back to the notes. With matched pairs, we are looking, if we want to block an experiment, we want to measure the difference in a drug versus a placebo, which is different than subtracting the means of each group. Likewise, if we were doing a pre-test, post-test match pair design, everyone would have a baseline pre-test measurement. Then they would get some sort of treatment. So if this was school, then you be taught the lesson. And then at the end, you would have the same post-test, and we would measure the difference in those two groups. Hence, the difference from person to person. So thinking about paired data, I want you to think about these. Consider the difference between men and women in the amount of time spent watching TV. Is that the same as comparing the difference in time between husbands and wives or brothers and sisters? Suppose you wish to study the effect of a patch on smoking cessation. Is studying one group with patch against an independent group without patch the same as comparing smoking reduction for a sample of individuals prior to the application of the patch and the same individuals after 6 months of using the patch? So what is accomplished with the pre and post test? And that's what statisticians will measure, especially researchers. What are we looking for pre-test, post-test data? So with paired data, if you know the data are paired, you must use the pairing. This seems obvious, but when you're trying to figure out which type of test we're doing, if you know that things are paired, this is your only option. You cannot run a test of two independent groups if you know the groups are not independent. So we will be doing paired data or doing this match pair design when the groups are not independent. To know if the data are paired, you must know how they were collected and what they mean. In other words, you just got to know. There's no test to determine whether the data are paired or not. There's no way we have to say like, oh, yep, this is paired, or these groups are independent, or nope, these groups are not independent. If we know the data are paired, we examine the pairwise differences. Because it's the differences we care about, we treat them as if the differences were the data, and we ignore the original two sets. So we'll see this in a couple of examples where we're just looking at the difference column as opposed to each individual column like we had before when we were comparing two samples. Now that we have only one set of data to consider, we can return to the simple one sample t-test. So for this paired data, we're looking for the mean difference, not the difference of means. Mathematically, a paired t-test is just a one sample t-test for the mean of the pairwise difference. You must indicate that your test is a paired t-test when you're describing the test. When we're talking about phantoms, you say, what is the test you're using? We're talking about a paired t-test. The sample size is the number of pairs, and we want to make sure that those are equal. If you have one piece of data where you only have one, we're going to call that an outlier. So only we look at the sample of pairs. And this means we are finding the mean of the differences. The mean of the differences as opposed to the difference of the means, which is what we found before. So be very careful with the language that you use when we're looking at comparisons. And again, this is for non-independent pairs. So what are our assumptions and conditions that we have to check? So our paired data assumption, now this is something, if we're talking about pairwise comparisons, we have to check that the data must be paired. With our independence assumption, the differences must be independent of each other, but the two groups definitely aren't. Randomness may or may not be important. If we are assigning subjects to treatment conditions, random assignment is important, like we talked about in Chapter 13. If we are studying the effect of a treatment before and after, randomness is not necessary. So if you're looking for a teacher to measure how well they taught the subjects, that you have a pre-test and a post-test, you're not randomizing who gets instruction and who doesn't. Everyone's just getting the exact same treatment. Likewise, with the 10% condition, when a sample is obviously small, we may not need to explicitly check this condition, but we will mention the 10% condition. Next, our normal population assumption. We need to assume that the population of differences follows a normal model. And we check this with a histogram or a normal probability plot of the differences from your matched pairs. So this is graphing the differences, or this is your NPP. And what is nice about a normal probability plot is it will always take x minus mean over standard deviation. And so when you do a normal probability plot and it gives you the slope, these two values are automatically calculated for you. So that's a nice little shortcut when you're trying to jump to the rest of the calculations we have to do. So the paired t-test. With the conditions met, we can test whether the paired differences significantly differ from an assumed value, and it's nearly always 0. So if we're trying to measure if there's a change or if there is a difference, our null hypothesis will nearly always be there's no difference. So we test our null and we say mu sub d, or the mean difference, is equal to delta naught. So that's pronounced delta, N-A-U-G-H-T, delta naught, where the d's are the pairwise differences, and delta sub 0, or delta naught, is nearly always 0. So similar to the difference in means, the mean difference that we're going to assume for our null hypothesis is nearly always 0. So we use the test statistic, our t-test. So we get a t-value of t n minus 1. Remember, this is your degrees of freedom, is equal to the mean difference minus delta naught over our standard error. And that's the standard for the difference over the square root of n, where n is the number of pairs. Our standard error for our mean difference is our standard deviation of our differences over the square root of n is the usual standard error for the mean applied to the differences. This is just like a one sample t-test. With confidence intervals for matched pairs, when the conditions are met and the null hypothesis is true, this statistic follows the student's t-model on n-1 degrees of freedom, so we can use n-1 degrees of freedom, so we can use that model to obtain a p-value. We are also able to find a confidence interval for the mean of the paired differences. So the confidence interval, much to what you would expect, would have our mean difference average, so our mean average of the differences, plus or minus our critical value of n-1 degrees of freedom times our standard error. The standard error, just like we said before, is the standard deviation for our differences over the square root of n, where n is the number of pairs, and the critical value depends on a particular confidence level C that you specify on the degrees of freedom n-1, which is based on the number of pairs n. As opposed to the number of samples you have, this is based on the number of pairs you have. And this is where you use inverse t to do your calculation. So with paired differences, consider the mean difference in age between husbands and wives. If we look at this paired box plot, the display tells us nothing about the husband-to-wife comparisons. The display comparing a group of wives against a group of husbands would simply be a comparison of men versus women. This comparison doesn't tell us anything about the difference between husbands and wives. But we are interested in the difference in age between a husband and his wife, so we're looking at the paired difference. So if we just look at this box plot overall, if we look at the average, the median Q1, Q3, 1.5 IQRs of both the wife or the husband, it's not really giving us much information outside of just men versus women and how old they are. But if we look at the differences in age between men and women, we get this nice looking histogram. So here's a histogram of the paired data. Each husband's age is compared with his respective wife's age, and the display of interest is the difference in ages. And what we can see is, if we do husband's age minus wife's age, and then we look at the total number, again, always label your axes, we see a nice uniform, unimodal, roughly symmetric distribution. where you have some differences in ages are up to 20 years to -12. Note how beautiful our distribution of differences is. We can use a normal model to find the probabilities. Pairing removes the extra variation present between the groups and restricts the variation to that associated with the difference in age for each pair. Pair difference is blocking. So a paired experimental design is an example of blocking. So words of caution before we do some examples. Using paired t-tests is only appropriate when the groups are somehow related. Be very careful to match data values for the two groups. If your groups are somehow linked, do not use a two-sample test. A two-sample test requires independent groups. You must know which condition, paired or not, exists when there is a comparison between groups. You cannot tell simply by looking at the data, so you gotta know. Do not neglect outliers. In the previous example, outliers are in the differences of ages between spouses, i.e., old fat rich guy, young lovely wife, or vice versa. So let's take a look at an example. One indicator of physical fitness is resting pulse rate. 10 men volunteered to test an exercise device advertised on television by using it 3 times a week for 20 minutes. Their resting pulse rates, beats per minute, were measured before the test began, and then again after 6 weeks. Results are shown in the table. And the question is there evidence that exercise on the device can reduce resting pulse rates? And if so, how much? So the question you need to ask yourself, are these two measurements, are these two columns independent of each other? And we can see that in a pre-test, post-test, these are definitely not independent measurements. So we need to conduct a hypothesis test. And we are looking for a decrease in mean pulse rates. So whether you want to write them as is the mean difference less than or equal to 0, or many of you are just going to write equal to 0. Is there no difference? Is the average the same? Our alternative hypothesis is the mean difference increased. So there's more of a difference. I want you to also note that if we do this, to find the difference, we would be taking before minus after. If you did the after and then you subtracted the before, we would be looking at the opposite inequality. So just as an aside, let's zoom in on the top. If your alternative hypothesis was that the mean difference went down, then what you're saying is that you're looking at after and you're saying that their heart rate decreased more than before, giving you a negative value. So always be careful how you write your inequalities. So the results, we can say, are independent from one pair to the next, but the measurements are paired by subject. So the before and after are definitely independent of each other. The samples are not randomly selected, but we're simply interested in the efficacy of the machine, so randomness is unnecessary. We don't need this for a pre-test, post-test. Likewise, 10% condition is also not relevant for the same reason. If we look at a histogram by jumping to our calculator, and we're looking at the differences, a histogram of the differences is sufficiently unimodal and symmetric. And if we look at the normal probability plot, it's sort of straight, so thus a normal model is appropriate. And so we set our normal with our hypothesized mean difference of 0 and our standard error, which is equal to our difference, standard deviation of our difference over the square root of n. And we know that we have 10 pairs, and so we use the values from the normal probability plot to get our average and our difference. So let's jump to the calculator now. We have our pulse rates for before and after, labeled in each appropriate column. Once I have those differences, I'm going to make a third column, let's call it the difference column, where I subtract before minus after. Once I do that, I can either do it in a spreadsheet, but in this case, I will do this in a calculator. We're going to run a t-test. So I'm going to hit Menu, Statistics, Tests, and I'm going to do a t-test. Our hypothesized mean is 0. We're going to use the difference list, frequency 1, and we're testing to see if the difference is greater than for our alternative hypothesis. When we hit calculate, we get a t-score, or a t-value of 3.5, a p-value of 0.0034, with our average being 2.8, and our sample standard deviation of 2.52, and a pair sample size of 10. So what calculations do you also have to do by hand? How do you get that t-score? Well, we write t sub 9 for the n-1 degrees of freedom is equal to the difference average minus delta naught over our standard error. So we have 2.8 minus 0 over 2.5298 over the square root of 10. That gives us our 3.5 t-score. If we want to know how we're comparing t to our critical value, we look at a t critical value with the degree of freedom of 9. So we hit Menu, Stats, Distributions, Inverse t. We're looking at a one-sided test, so our alpha level is 0.95, comma, 9 for our number, or degrees of freedom, and we get 1.8331. So what our p-value is saying is what is the probability that the average in our sample is greater than or equal to 2.8, or what is the probability that our t-score is greater than or equal to 3.5. And when we do that, we get a p-value of 0.00336. Since the probability is small, we reject the null. And we say there is sufficient evidence to conclude that exercising with the fitness equipment may reduce resting pulse rates. To finish this problem, it also asked you how much of a difference there is. And since we reject the null hypothesis, we will find a 90% confidence t-interval for the actual mean difference in resting pulse rate. We have met the conditions for a 90% confidence interval with our normal model with our average of 2.8 and our standard error of 0.8. So we'll use the same critical value, 1.8331, that we found previously. We're going to write out our confidence interval, which is the average difference plus or minus our critical value with n-1 degrees of freedom times our standard error. So we have 2.8 plus or minus 1.8331, which is our critical value with its degree of freedom of 9. 2.52 is our standard deviation for our differences over the square root of 10, which is the number of pairs. So we get 2.8 plus or minus 1.4665. From our calculator, we go Menu, Statistics, Confidence Intervals, and we're doing a t-confidence interval. We're going to select our data, which is our differences. We have one frequency, and we're doing a 90% confidence interval. So we are 90% confident using the exercise equipment for 6 weeks may decrease resting pulse rates between 1.3 beats per minute and 4.3 beats per minute. That's the interpretation that you need to do. So we're going to cut it right here from our first example. We have one more example left to cover, and then we're done with Unit 6.